Hello everyone, this is Miss Lindsay. Today we're going to talk about 15.2, dealing with permutations for special counts. Let's go ahead and continue on from what we learned in 15.1, dive into our first example here. Galinda has forgotten Kelly's phone number, but she remembers that each of the 7 digits is either a 7 or an 8. How many phone numbers are possible? So again, phone numbers, the order does matter. So we're thinking about a permutation here. The other idea that you can do is that you definitely know there's 7 digits. So we know we have 7 spots here. So how many options do we have for the first spot? It could be a 7 or an 8. So we have 2. And then again, we have options 7 and 8 for each of these spots. So by the fundamental counting principle, we would have 2 for each of these spots because we can have the options of 7 and 8 for each of those numbers. This is also equivalent to 2 to the 7th power, which gives us 128 possibilities. Next example. In how many different ways can a sequence of 4 cards be dealt from a full deck of 52 cards without replacement? So we're talking about a sequence, so again we're referring to order and permutations. We have a total of 52 cards, so we have 52 cards and we're selecting 4 of them and we're not putting them back. Or in other words, if you'd like to go ahead and write out the 4 different spots, we have 52 options for the first one. Bring it down by 1 each time, which is again the same thing as 52 P4, and we get 6,497,400 different ways this can occur. Or number 3, how many different ways can a sequence of 4 cards be dealt from a full deck of 52 cards with replacement? So slightly different, with replacement after each card is drawn. So similar to number 2, but we change it up and we now have with replacement. So in this case, we have 4 spots. How many options do we have for the first one? Well, we have 52. Now we're going to put that card back in. So each time we would have 52 options. So again, that would be 52 to the 4th, which would give us 7,311,616 ways this can occur. Number 4, how many different ways can a sequence of 4 cards be dealt from a full deck of 52 cards without replacing if the first card must be a jack? So again, it's a sequence, so we're referring to order. We have 4 different spots that we're trying to fill. The first one must be a jack. Out of 52 cards, there are 4 possible jacks. We are not replacing that card. So from a full deck of 52, we took 1 jack, then we have 51 options from there. And that again must decrease each time by 1. So we have 4 times 51 times 50 times 49, which gives us 499,800. Okay. Number 5. Find the number of permutations of the letters in the word entrepreneur. So again, order matters here. This is slightly different because this has to deal with repeated objects, or in our case, for our example here, it's repeated letters. You'll hear me say that a lot, repeated letters, because specifically we do this type of problem quite frequently, but it can be any type of repeated objects. So when we're looking at the word entrepreneur, we have a total of 12 letters. Some of those are repeated. For example, if you look at just the first letter, we're looking at E. E is repeated 4 times. So we actually have permutations for repeated objects. We have the number of permutations of n objects with r objects alike. So we have r like objects, s of another alike objects, and t of another is given by n factorial over r factorial times s factorial times t factorial. So these are your, in the denominator, these are your repeated objects, or again, in our example, repeated letters. So if we're going back to example 5, the total number in the numerator would be 12 factorial. Now we have to go through and see, okay, E was repeated 4 times, so that's our first repeated letter. Then we also have N, which is repeated twice, so that's 2 factorial. And our last repeated letter would be R, and that occurs 3 times, so that would be over 3 factorial. So let's go ahead and get our calculator. Move this over so you guys can see that. Very important in order of operations how we are going to enter this into our calculator. So we'd have 12 factorial, so 12, then you go to math, highlight PRB, number 4 is your factorial, divided by, really important that you put parentheses around the entire denominator. So you're dividing by 4 factorial, 2 factorial, 3 factorial, the multiplication of those, and not simply by 4 factorial. So again, I'm entering all of these in. So I've got 2 factorial, 3 factorial, go to math, PRB each time, number 4 to get your factorial. So you can see I have 12 factorial divided by the 4 factorial times 2 factorial times 3 factorial. So in that case, when we push enter, we will get our answer to be 1,663,200. Again, let me point out, very important in your calculator that you put parentheses around the denominator so you're following the correct order of operations. Example 6, again, another special count here. Find the number of permutations of 5 people around the table. Now we are assuming this table is circular. Okay, so this is called circular permutations. And how we would go about doing this is by using the formula n factorial over n, or simply n minus 1 quantity factorial. So the quantity of n minus 1 factorial. And the reason for this is what we're going to do is we fix a person or an object at a spot. And then we arrange the other objects according to that fixed spot. So in our case here, we have find the number of permutations of 5 people around the table. We're going to fix one person. So that will be the quantity n minus 1 factorial. So in our case, 5 minus 1 factorial, which is equivalent to 4 factorial, which is 24 permutations on that. Okay, so this concludes section 15.2 notes.